Hello, and today we're going to learn how to write the equations of piecewise functions. Um, the, kind of what you see here is what we're going to be doing. So if you take a look, this is kind of a cute way of doing it, but here I have a picture of a smiley face. So to write a piecewise function, what I would do is I would say the name of the graph, so I'm calling the graph smiley face, and then equal to, and then I list all the different pieces that make up the graph. In this case, I've determined four different pieces that make up the smiley face. One is the eye, one is the left side of the smile, one is the right side of the smile, and then one is the right eye. And then after each piece, I write where it happened. So where does the eye occur? And specifically the x values. So the eye occurs where x is equal to -3. The left side of the smile occurs when x is between -2 and 0. The right side of the smile occurs between 0 and +2 for x, and then the right eye occurs where x is equal to 3. This is a great just like little way of understanding what each of the pieces of a piecewise function stand for. This is the name of the entire graph, this is the piece, and then this is the location where each piece occurs. Okie dokie? So to get a little bit more technical, the name of the graph or the name of the function usually appears in the vertical axis. So whatever the vertical axis is labeled as, if it's y, you're going to say y equals. If it's f of x, you're going to call this f of x equals. But we need a name for the graph. And then we're going to list the different pieces, the different individual shapes that we see, or line segments, whatever that we see, and then the position at which they appear. This has to do with the x value. So where are the x values where each of these pieces occur? All right, let's take a look at an example. So we're going to start off with an easier one. It looks like two different linear segments joined together. So we're going to try to write the piecewise equation of this entire graph. Now to start, we need a name for the graph. If we look at the vertical axis, we can see it's labeled as y, so we're going to call this y equals. And then we're going to put that little curly bracket here, and then this is where we're going to list out the different pieces. So the first piece I see is this linear segment right here. So I need to list the expression that makes this linear segment. With linear segments, I need a slope and a y-intercept. If I have both of them, I can write the expression. So the slope of this thing goes down 1 over 1, down 1 over, and down 1 over. It looks like it's -1. So it's -1x, or we can just write that as -x. Okay? And then the y-intercept we can clearly see as being 3. So that's -x plus 3. Okay? Before we move on to the position, let's just look at the second piece. So this is the second piece of the piecewise function. Part 2 is what it's called here. I need a slope for this. So it looks like if I go, let's see, up 1, 2, and over 1, up 1, 2, and over 1, 1, 2, and over. It looks like it's up 2 over 1, which would be a positive slope of 2, so that'd be 2x. Now, y-intercept. It's not going to be easy to see because I don't see it crossing the y-axis. So I need to figure this out mathematically. So for piece number 2, or part number 2, however you want to call it, doesn't matter. I need to figure out what the y-intercept is. I can do that by saying piece number 2 is y equals 2x plus b, because remember b is what we use to represent the y-intercept. So not knowing what b is, I can take any point on the line and substitute it in for y and x. So I don't know which one we want to choose. We can choose this one right here if we want to. This is 4 comma -1, where 4 is the x value and -1 is the y value. So I'm going to put in, or substitute, -1 for y and 4 for x. And then I can solve for what the y-intercept is. So this is negative, oops, let me just erase that, do this, yoinks. Got rid of that too, eh? Okay. So I can draw out the parentheses here, -1. Here the parentheses would mean multiplication, so that's 8 plus b. And if I subtract 8 from both sides, I would get -9 is equal to b. So I've just figured out what my y-intercept is. It would be -9. Now, just because I don't see it actually hit the y-intercept here doesn't mean that it wouldn't exist if we were to continue to expand leftwise and rightwise, okay? So this is the equation or the expression that represents this linear segment. Another way to think about it is y equals -x plus 3, which is this one right here, and y equals 2x minus 9. Now, these are not lines, they're line segments, so we have to write the x values where they appear. So the blue part, part 1, only appears when x is between 0 and 4. It looks like 0 is included because there's a solid dot on here, and at 4 it looks like the red one is the one that's included there. So we're not going to include the value of x being 4 for this piece. Okay, so x has to be between, remember, just x values, between 0, so 0 less than or equal to x is less than, I'm not going to say equal to because it doesn't look like the blue's on the 4. It looks like it's the red that's on the 4. So, to summarize, we have y being the name of the graph. Negative x plus 3 is this part right here because the slope is negative 1 and it crosses the y-axis at 3. And then the x value is where that piece occurs. It occurs between 0 to 4. I'm just going to draw this. This is not something that you really want to draw on your piece of paper, but just for illustrative purposes. That's kind of what we're talking about when we say where does it occur. It occurs between 0 and 4, and it doesn't look like there's actually a blue dot on 4, so we're going to leave that open. It's not inclusive of 4. Now, for the red one, we need to include the x values where the red thing exists. So it looks like it starts at 4. So x starts at 4 and goes all the way to 8, and it includes 8 as well. There's a solid dot at 4, a solid dot at 8, so x is everything between 4 and 8, and it includes both 4 and 8. So x is between 4 and 8. Okay, that is the piecewise function for this graph right here. And again, let me just erase this because, like I said, this is just for illustrative purposes. This is not actually something you would actually do. It's just for me showing stuff. So we have y equals, y is the name of the vertical axis, therefore it's going to be the name of this graph. Y equals the blue part, which is negative x plus 3, only existing between 0 and 4. And then 2x minus 9 is the second part that only exists between 4 and 8. Okay, let's try a different one where they're not connected. These actually seem a little bit easier to me, but you will determine yourself whether they're easy or not. First, we need the name of this graph. Now, if you look on the vertical axis, it's actually calling this f of x, not y. No biggie, so our name is going to be f of x. F of x equals. Okay, we need that little curly bracket. We have two pieces. We have a blue and a red again. So for the blue part, we need the equation of this. All right, so let's see. It looks like if we go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Yep, it looks like the slope is positive 2. So positive 2x. And then we need the y-intercept. It looks like this thing crosses at 1, and it does, like right on 1. If it wasn't right on 1, we would have to actually figure it out the same way we figured out the previous one. So 2x plus 1 is this, this piece right here. And we'll write the location in a second. Okay, the red piece right here, what's the equation of this? Looks like it's up 1 over 1, up 1 over 1, up 1 over 1. Hey, that's a slope of positive 1. We could just call that, instead of saying 1x, we can just say that's positive x. And where would this thing cross the y-axis? Well, in this case, I might be able to do one of two things. I can do what I did before, which is if I'm looking at part 2, I can make an equation for it. Y equals x plus, and I don't know my b value. And then I can substitute in any point on here that I want. So in other words, I can say this one, which is the x value is 5 and the y value is 4. So this is 5 comma 4. I would substitute a 4 for the y, a 5 for the x. And then there's no need for the parentheses. I'm not multiplying anything on the outsides of them. I could just subtract 5 from both sides, and I get negative 1 is equal to b. So that's one way of doing it. Or, because this is actually so small and the graph extends way well beyond it, I can kind of trace this. This is a slope of 1. So if I were to continue going this way, down 1 over 1, down 1 over 1, I can see that it would have crossed at negative 1 if it were allowed to be a full line. Keep in mind, this is a line segment. It ends here. It starts here and ends here. If it was a line, it would go on forever in both directions. So when we're trying to find the y-intercept, the b value, we're trying to figure out if it were allowed to extend in both directions, where would it cross the y-axis? So that would be negative 1. So again, I can do it visually just by using the slope to count backwards, or I can use substitution. Write this, use a variable for the y-intercept, and then just substitute a value of y and x, and then solve for b. In any case, I end up getting that this is x minus 1. So this graph is x minus 1. This graph is 2x plus 1. Now, I need to write the locations where they appear. So this graph, part 1, only appears when x is between negative 2 and positive 2. There's a solid dot on here, which means x is allowed to be negative 2. And there's an open dot here, which means that x is not allowed to be 2. It's up to, but not including 2. We write it this way. So x is between negative 2, inclusive, which is what that little line there is for, and 2, non-inclusive of 2, so we don't put a little line under there. Now, we need the location for the second part. The second part starts at 2, and there's a solid dot, so it's inclusive, and goes all the way to 5, it looks like, and again, that's inclusive as well. So again, we would have both endpoints for part 2 being inclusive. So it goes from 2, x is between 2, inclusive, and inclusive of the endpoint, which is 5. So you might be noticing that for our location, it's always just x values. It's the equation or the expression that represents the lines, and then just the x values where those things exist. Okay. All right. To finish off, let's do a more complicated one. We're going to do one with 3 pieces, and there's no color coding, so we're going to have to kind of, which is what you would probably get on your paper anyway. So we're going to have to kind of look at this without the colors involved. Okay. First, we need the name for the graph. It looks like the vertical axis is called y, so we're going to call this y equals. Side note: if you don't have your axes labeled, you can choose y or f of x. Those are usually the two that we see, either y equals or f of x equals. If it is labeled, you have to use whatever the vertical axis is. If it's not labeled, you can choose one or the other. Okay. All right, now we have 3 pieces here, it looks like, right? We have this line. It's actually a ray because it starts from a point and then goes infinitely in one direction. We have a line segment right here, and then we have another ray right here. So we're going to have 3 pieces, okay? They're not color-coded, so I'm actually not going to color-code this. We're just going to go from left to right. And in actuality, to keep everything okay, let's just do it this way. So going from left to right, we have this one piece right here, okay? So we need the equation for this. It looks like if I were to pick a point, go up 1 over 1, up 1 over 1, up 1, it looks like the slope on this thing is positive 1x. So I can start off with x. And does it cross the y-axis? It does. It crosses it at 3. So the b value would be x plus 3. Okie dokie. Now, actually, because this isn't color-coded, and to be honest, this is how I would probably do it on if I was given this, I'm actually going to write the x values where they occur. Now, this arrow means it keeps going to the left forever, which means that it's not bordered on the left side. The only border happens on the right side. So this thing goes from, we'll call it negative infinity, all the way up to 1. There's a solid dot here, but we don't know whether it belongs to the left side or the right side. You can choose which side it belongs to. So, I don't know, let's just include it with this first piece right here. So it looks like x has to be, it's between infinity, negative infinity, and it's less than and including 1. Now, we don't usually write the infinity. We just say that x is less than or equal to 1. So that means that everything from 1, solid dot, all the way over to infinity is part of the x values of this thing, which is true. All right, I'm going to erase that. Just wanted to show you kind of visually why I'm choosing x is less than or equal to negative 1, or why that is the right way to do it. Okay. The second piece is this linear piece right here, this linear part segment. So we need a slope for this. It looks like, if you notice, these 2 dots are only 1 away from each other. So if I go down 1, 2, 3, 4, 5, 6, and over 1, that would be a slope of negative 6. So we have negative 6x. And now we need a y-intercept. So does this thing cross the y-axis? Not in the segment. And notice that because the slope is negative 6, it might be kind of a pain to go all the way up because it goes off the graph. This is what I would suggest for piece 2, and I'm going to do it over here. For piece number 2, trying to figure out what that y-intercept or that b value is. So y is equal to negative 6x plus whatever the y-intercept is. We don't know what it is. Let's take a point and substitute it in. Let's pick the point 1, 4. So 4 is the y value, and 1 is the x value. Okay. There's nothing to do with the parentheses over here. Here, negative 6 times 1 is negative 6. Okay. We have to add 6 to both sides. We end up getting that 10 is equal to b. So this is 6x plus 10. Now we need the boundaries. Okay, that solid dot we included with the left one, so we are not going to be able to include that 1 with this one. And it ends at 2. Again, we have a solid dot here. Do we want to include that one? Because we haven't assigned that a line segment yet. So yeah, why not? Let's include that. So x is between 1 and 2. Doesn't include 1 because that dot belongs to the first piece. And we'll include that second dot with the second piece. Okay. Now all we need is the third piece, and we have the entire graph of y. Third piece, let's see. The slope looks like up 1 over 1, up 1 over 1, up 1 over 1. Yep, we have another slope of positive 1. So it's x. And then what's the y-intercept? So this is actually one that we might be able to just trace backwards. If we notice the slope is 1, so if you go backwards, down 1 over 1, down 1 over 1, down 1 over 1, keep going, down 1 over 1, down 1 over 1, this would cross at negative 4. So this would be x minus 4. Just to show you I'm not crazy, I'll actually do it out algebraically. So if we have to solve algebraically for piece number 3, okay, we know that it's x, the slope is 1, so it would be y equals 1x plus something, call it b. We don't know what it is. And then just pick any point that's on the line. So this point right here, which is 2, -2, would work. So my y value is -2. My x value is 2. I don't need the parentheses because I'm not multiplying anything, so we can drop them. And then if I subtract 2 from both sides, I'd get -4 is equal to b. So just one way to do it is to trace backwards. The other way is to solve algebraically, which means write out what you have, put in a variable for the y-intercept, and then choose any point on the line, plug it in, and then solve for b. In any case, I get -4. Now I need all the x values that exist here. Well, here the left boundary is 2, but I already included 2 with this, which means I'm not going to want to include 2. And there is no upper boundary. So all of the x values here, just everything that's greater than 2. Not including it, because again, this went to piece number 2. The solid dot went to piece number 2. So x has to be greater than 2. And not less than anything, because this arrow means that it keeps going on forever in the right direction. Okay? Okay, well, I hope that makes life easier on yourself. Again, just to reiterate, so to write a piecewise function, you need there are 3 parts to writing the equation. One is what you call it, and it's usually defined by just what the vertical axis name is. If it doesn't have a name there, it's usually going to be either y or f of x, and in that case, you can choose. If they say function, it's better to use f of x because that's just the notation for a function. Equals, we have the curly bracket, and then the second part is the individual pieces. In this case, in the last one, we had 3, so 3 pieces. We're going to have 3 different parts. This line, which actually is a ray, this line segment, and then this ray right here. So we have 3 little pieces of the graph. And then the positions, the x values where they exist. So this piece right here only exists when x is less than 1. So all of these over here is this first piece. Between 1 and 2, that's where this one exists. And when x is greater than 2, that's where this exists. And that's all there is to piecewise functions. So I hope this helped.